SwayamPrabha. Digital India. Educated India.
Hello all. In this video we will be looking at the composite materials and what are the different types of composites available for structural purposes. So, just to give a recap of previous video, we discussed about what exactly are composites, how composites are different from their constituent materials, which we said are the matrix and the fiber. So, let us see a brief outline about what we are going to discuss. We will start with different composite materials. So, we will focus on what are the different fibers available, matrices, materials available, as well as the fillers which may not improve the mechanical properties, but there are other properties which they can modify. After that, we will be looking at different kinds of composites. Here we will be focusing our attention only on the fibrous composites. And lastly, we will try to pictorially see how we can classify all these composites and have a mental picture about where a particular composite fits in the bigger scheme of composites. Okay. So, let us recap what we discussed about fiber reinforced composites. We said this composite has three major constituents, saying the fiber, matrix material and the filler material. We said fibers are the load bearing materials in the composites, primarily because they have good strength and stiffness. But then we simply cannot have these fibers because then they are very fragile, especially when we apply transverse loads. That is why we need a matrix material to hold these fibers together. So, in addition to holding, they do several other benefits, such as transfer and distribution of loads is better done with the matrix, and then it also improves the ductility, toughness and the electrical insulation. And lastly, we mentioned fillers are there to enhance other properties in addition to the mechanical properties. But now let us dive into each of these materials and see what are the different options we have for choosing a particular composite. So, starting with fiber materials, we start with glass. Glass is a very commonly used fiber material in structural composites, primarily because of its low cost, but the reason why we are using is because of its good strength. And the way it is produced is by drawing using the molten glass. There are several varieties of glass fibers. Two commonly used glass fibers are the E glass and the S glass. E glass is more commonly used because of its low cost, but later this was improved through S glass, which has superior strength as well as stiffness compared to E glass, but the pitfall of it is it is slightly expensive. The E in the E glass represents the electrical properties. So, composites made up of these glass fibers are usually called GFRP, standing for glass fiber reinforced plastic. Okay. So, in addition to glass fiber, we also use carbon fibers, or sometimes also called as graphite fibers, depending on the carbon content. Usually when we say carbon fibers, the carbon content is less than 95%, but for graphite fibers it is even more, about 99%. So, these are a bit expensive and mostly used for some specific applications where one can afford these high costs. The reason why people use carbon fibers is primarily because of its very good strength and stiffness even compared to the glass fibers. So, the way it is produced is by pyrolysis, where it converts the precursors or the raw material into carbon. So, the various precursors used in the industry are polyacrylonitrile, which we in short call it as PAN, PAN, and pitch. So, the difference between the graphite and the carbon is, for graphite it is subjected to very high temperatures to get high concentration of this carbon. Later we will see how the carbon properties compare with the glass in few minutes. Third category of fiber material is aramide, commercially known as Kevlar, produced by DuPont. These are most popular because of their applications in bulletproof jackets or ballistic protections. They have two big advantages, one being very high specific strength, and secondly, more importantly, high failure strain, which means they can take large strains before failure, which in other words means better ductility. In general, like the glass and the carbon fibers are considered to be brittle, meaning they take very less failure strain. But compared to them, aramide can take large failure strain, which means they are more flexible and they can take more energy before failure. But one disadvantage with aramide is they are not suitable for high temperature applications because of their discompatibility. So, in addition to these, we also have boron fibers. Usually boron is just a coating on a tungsten or a carbon core, which means it is itself a composite because it is made up of two materials, one the core made up of tungsten or carbon and upon which we have this boron coating, and usually these are relatively large diameters. So, usually other like the glass, carbon and the aramide, those are in the couple of microns ranging from 5 or 10 microns, but whereas in the carbon the size can go as well as 50 to 200 micrometers. So, these are much larger compared to other fibers. Because of the large diameters, they are less flexible and they also exhibit the brittle behavior. Though they are stiff compared to other fibers, one disadvantage of boron fibers is they can develop some residual stresses, especially because of the mismatch in the CTE with the fiber and the matrix material, or even between this the boron on the tungsten carbon core. So, the commonly used boron composites are these boron epoxies as well as the boron aluminum composites. Depending on the applications, we can also have polymer epoxy is the polymer matrix and aluminum is the metal matrix. And lastly, we also have silicon carbide fibers which are specifically used for high temperature applications. So, this concludes the 5 commonly used fibers used in composites. Now, let us try to summarize what we have learned about these fibers and see how each of these are relatively good in the specific stiffness and the strength. For this, we will start with a reference of aluminum. Let us say aluminum is somewhere here showing the specific strength and the specific stiffness. So, starting with glass, we said there are two varieties of glass, one is the E glass and the other is the S glass. So, E glass is somewhere here, meaning that the specific strength is much higher than aluminum, but the specific stiffness there is no big difference. So, this is let us say E glass. And next we said S glass has superior properties compared to E glass, these are somewhere here, meaning the specific strength is improved, but specific stiffness also there is an improvement, but not very significant. So, next we move to the carbon fibers. If we recall, carbon is made from two different precursors, pitch as well as the PAN. So, let us say here is the carbon fibers made from pitch, but the carbon fibers made from PAN are somewhere here, meaning the carbon fibers made from PAN have very high specific strength compared to the glass fibers, but if we compare with the specific stiffness, there is an improvement, but not too high. But whereas if stiffness is a requirement for a particular application and strength is okay, then we can go to the carbon fibers made from pitch, because their specific stiffness is much higher, not just with the metals, but also with the compared to glass. So, usually I am just showing it through a point, but of course, there is always a variation in the properties, because especially these being made from polymers, there is always a scope for change in the properties based on the manufacturing methods used. Okay. So, after this we move on into aramid fibers. Aramid fibers are somewhere here. So, meaning that they are in between the glass fibers and the carbon fibers, especially with PAN, where the specific stiffness is intermediate as well as the specific strength. And lastly is the boron fibers. Boron fibers are somewhere here, where the specific stiffness is much high compared to the glass, but not as high as the carbon fibers made from pitch precursor. So, this should give a summary of the different properties of different fibers and how they compare with each other. As we can see, depending on the application, if stiffness is the only criteria, then one should go with carbon fibers made from pitch or the boron fibers. But if specific strength is a major criteria, then either we go with the carbon fibers made from PAN or the aramid or the Kevlar fibers. So, after this let us now see into matrix materials. So, in matrix materials, these are made with polymers, metals and ceramics. So, the way we will present it is to see how the matrix materials are resistant to temperature. So, we will start with polymers, which are the least resistant to temperature, meaning the operating temperatures we can go are the least with the polymers, and then we will see the metals are better than polymers and ceramics are better than both polymers and metals. So, here we are mentioning that with polymers, the maximum temperatures one can go is 450 degrees centigrade. It is not like all polymers can go there, but there are some specific polymers which can reach that. But even in the polymers, there are different matrix materials one can choose based on whether we are looking at thermosets or thermoplastics. So, thermosets, for example, like epoxy is a very commonly used polymer matrix. You will see to the rest of the course wherever we discuss, we talk about either glass epoxy composites or carbon epoxy composites. But in addition to the epoxy, we also use this polyester thermoset matrix material. But when it comes to thermoplastics, two commonly used matrix materials are PEEK and PPS. PEEK stands for polyether ether ketone and PPS stands for polyphenyl sulfide. So, usually for epoxy, the glass transition temperatures are somewhere around 170, 180. So, which means the operating temperatures can at most go below the glass transition temperature. So, there are some epoxies where we can achieve these high glass transition temperatures, and the operating temperatures for these epoxy based composites can go as much as 150 degrees centigrade. But using PEEK and PPS, these operating temperatures can be little stretched to close to 315 degrees centigrade. But if the operating temperatures are much higher than this, then we prefer to go to metal matrix composites, where these metals can be lightweight metals such as aluminum, titanium and magnesium, where the temperatures now can go as much as 1250 degrees centigrade. So, the advantage of using metal is definitely they are good in strength and stiffness. We probably are not talking about specific strength and stiffness, but we are mentioning about the absolute values of strength and stiffness, and compared to polymers they are more ductile. But if the temperatures are even more like beyond this 1250, then and second option we have is to go with ceramic based matrix materials such as the silicon carbide. So, though they can take high temperatures, one disadvantage with these ceramic matrix materials is first they have very poor tensile properties, meaning they are good in compressive loads, but when tensile loads are there they are not good enough. And the other thing is they are brittle, meaning they fail without much warnings. So, but there are still options available if the temperatures go beyond this. One of the example is carbon fiber carbon matrix, where both the fiber and the matrix materials are made of carbon, and in these conditions it can go to temperatures to about 2700 degrees centigrade. But these are only used in very critical applications where the high costs of these materials can be afforded. These high costs are because it is a multi-step procedure and the manufacturing methods are much more sophisticated. So, now that we have seen the different matrix materials and the fiber materials, the third and the final component of the composite is the filler. So, we already mentioned fillers are not here to improve the mechanical properties, because mechanical properties are taken care by either the matrix or the fiber, but fillers are here to improve some additional properties. So, let us see some common fillers and what properties do they improve. So, the first we start with is hollow glass microspheres. Mostly they are used to reduce the weight, meaning since they take more space and because of the voids the density of the composites is now lesser. We could also add clay or mica to decrease the cost of the composites. And carbon black is also commonly used to protect from UV. Let us say we are developing these composites which are exposed to UV rays coming from the sun. Then when the prolonged exposure to UV, what happens is that UV energy can break these polymer chains in the polymer composites. So, to protect against this UV degradation, we can add carbon black, which lengthens the life of these composites. There are also applications where there is a fire hazard where the composites are used. Then we can add these aluminum trihydrate, which is resistance to either flame or smoke. So, these are some of the fillers commonly used in the industry, but of course, we are only looking at a small subset of a bigger basket of fillers and other materials for fibers and matrix materials. So, as we will see, composites is an area which is evolving. So, meaning like the composites which we use today are much different from what we have used 5 years back or 10 years back, because now we are coming up with new matrix materials, filler materials as well as the fiber materials. So, this should complete the first part of this video where we are looking at the different materials used in the composites. Now, we move to the second part where we are looking at different kinds or types of composites, meaning what are the different forms in which we see composites and how we use it in the structures. So, let us start with unidirectional lamina. Unidirectional meaning these fibers are all in a same direction parallel to each other. So, let us say this is a single layer of the lamina, and let us say now we have these fibers all in one direction. Let us say this is the cross section of the fibers we are looking at. and these are all in along the length. So, sometimes lamina is also called as ply, and unidirectional, in short we are calling it as UD. Later in the course we will come back and use this more often. So, just to remind you, we are focusing on fibrous composites where we use fibers to prepare the composites, and specifically we are looking at a continuous fiber, meaning the same fiber will go from one end to the other. These are very long fibers, and so the advantage of this is they definitely have good stiffness and strength, much greater along the fiber direction. But in the perpendicular direction to the fiber, the transverse direction properties are not superior, meaning along the fibers they are strong and stiff, but to the perpendicular direction or the transverse direction, these properties are not so great. The second category is the woven fiber composites, where now we have two fibers in perpendicular directions. They are also called as bidirectional lamina, in short BD, BD standing for bidirectional lamina. So, since we have these perpendicular fibers, we have to weave them, and these weaving patterns, there are several available, and each weaving pattern has few advantages and disadvantages. Because of the limitations of the time, we are not going into them, but let us see how are they compared to the first category, which is the unidirectional lamina. So, we see that the properties are a little compromised compared to the unidirectional. The reason is because of the weaving, these fibers are no more straight. Since they are no more straight, these properties along the length of the fibers are a little less compared to the unidirectional lamina. So, if you are just looking at the mechanical properties, then the unidirectional laminas are good. But if we compromise a little about these properties, the good thing about the woven fiber composites is these properties are good in both the direction, both along the direction of the fibers or the primary fibers, and even in the perpendicular direction, since there are enough fibers. Now, the properties in the second direction as well are superior. So, usually a good example for woven fibers is the shirt material or the clothing materials, because as we can see there we have threads going in perpendicular directions. So, then moving now to the third category is the laminate. So, the first two categories are single layer materials. But laminate is a multi-layered material, meaning we either use the unidirectional lamina or the bidirectional lamina and stack them together. So, once we stack them, we bond them together to form what is now called as the laminate. Since we are stacking different layers, it could be in reality, in real applications, we can have as much as 30 to 40 layers as well. Now that we are stacking these layers, now we can choose, we can vary the material in each of these layers. We can also vary the thickness of each of these layers as well as the orientation. Orientation meaning, let us say in the first layer we can have 0 degrees, meaning all of these fibers are at horizontal. Maybe in the second layer we can have it in the perpendicular direction, or maybe the third layer it could be inclined, let us say 45 degrees. So, which means we can vary the orientation, the angles 0, 90, 45, and we can also vary the thickness. So, meaning the first layer and the second layer need not be the same thickness. Moreover, we can change the material as well, and lastly we can vary the sequence, meaning let us say the first layer if it is 0, then 90 and then 45, I can also with the same 3 make up something like first starting with 0, then 45 and lastly the 90. So, the sequence also we will see later in the course that the properties or the effective properties of this laminate will greatly depend on which sequence we are using to prepare the laminate. So, though it has many advantages, one small disadvantage is it is susceptible to delamination. What is delamination? Delamination is the failure between two layers. So, previously we said we are bonding several layers or stacking them together to make these laminate. But usually what happens in applications or real applications is most often the failure is the between these layers, because that is where you only have the matrix material or a simple polymer or an adhesive to bond this. Since there are less fibers there, it is much prone to failure, and that failure is what we call it as delamination. Since we are discussing about delamination, one more point is when we talk about woven fibers, these are less prone to delamination. The reason is because it is made up of a single layer, and then this weaving also nowadays there is automated machines which can do 3D weaving, meaning these weaves, instead of going just with one strand, they can go deeper into few layers of fibers and then come back. So, meaning that there are those are fibers to take care of to prevent the delamination in case of woven fiber composites. So, on this slide we have seen both single layer and multi-layer composites, but in addition to this we have few more composites, something called as the chopped fiber composites. So, the major difference is in the previous slide we have seen all composites are made up of continuous fibers, but something like glass fibers and the glass carbon fibers, they can be chopped into smaller lengths, and once they are chopped into smaller lengths, we can add it to the matrix material and then mold it. So, basically then we can use the molding fabrication methods to prepare mechanical components such as the machine parts, gears and the valves, and there are many other applications where people use these chopped fiber composites. One big advantage of them is they are less expensive compared to the continuous fibers, because the manufacturing cost involved to prepare those continuous fibers is much more expensive, and as well as the fabrication methods, now that we are using molding, that also reduces the cost. But one major disadvantage of using chopped fiber composites is these properties are relatively poor, and we can now understand why these properties are poor, because if it was a continuous fiber it can take loads, but now that there is a discontinuity, this load should again transfer from the fiber back to the matrix and again from the matrix to the second fiber or the third fiber, which means matrix now becomes a weak link in this while taking the loads, and that might be one of the reasons why chopped fibers are not used when loading is a primary design criteria, but they are used when you need intermediate properties and then the prices are less. So, in addition to the chopped, we also now have an hybrid composite. Hybrid has, the name as we can see, it is a mix of few things. But there are two big categories in these hybrid composites. One where we say more than one fiber is used. So, meaning like you can have both carbon and Kevlar, or maybe carbon and glass, depending on the application we choose. The second category of hybrid is where we have a combination of continuous and chopped. So, for example, the figure shown here, right, it shows both the chopped fibers as well as these continuous fibers. So, these two categories of hybrid composites where we are saying either we can have two different fiber materials, two or more, as well as mix of both continuous and chopped. One example where we use these multiple fiber materials is again Kevlar and carbon, where we try to bring the good things from these two different materials. From Kevlar we know that it is good under tensile loadings, but carbon is good under compression loadings. So, where applications you have both tensile and compression, having both of them will take care of both loading scenarios. So, this should summarize the different types of fiber composites which are commonly used in the industry. So, we will try to show all the composites and see how are they related to each other. So, the broad classification can start with fibrous and particulate. Meaning these either we can use fibers or we use particles. So, whenever we talk about adding nanoparticles, right. So, those are also composites and sometimes called as nanocomposites because we are using nanoparticles to reinforce the polymer or reinforce the composite. So, this could be CNT, CNF, carbon nanofibers or carbon nanotubes. And of course, we are not only talking about nanoparticles, but they could also be millimeter size or sub-millimeter size particles such as the silicon carbide particles. But in this course we are focusing more on the fiber reinforced composites. So, in fiber reinforced composites we have two categories again. We have the continuous fiber and the chopped fiber. So, even in the continuous fiber we have just seen that there are two other categories, either we can go with a single layer or a multi-layer. So, the other name for this multi-layer is the laminate. But again in the single layer we showed that there are unidirectional and bidirectional. UD or the unidirectional as well as BD the bidirectional or also called as the woven composite. Okay. So, when we add these unidirectional or the bidirectional composites, we can then go into these multi-layer laminates where we stack up these individual layers. Individual layers, I think previously we said they can also be called as lamina or ply. Okay. I think this should give some idea about this composite, saying if we come across a new composite, we should be able to picturize where it fits in this scheme of classifications, saying that we started with fibrous and particulate. In the fibrous we are talking about the continuous fiber and the chopped fiber, but most composites or the most structural composites are made up of these continuous fibers, which could either be a single layer or a lamina or a multi-layer or the laminate. So, now let us summarize what we have discussed in this video. We started with these composite materials starting with fibers. The more commonly used fibers are these glass, carbon and aramide. Sometimes we also use these boron fibers as well as the silicon carbide fibers. But moving to the matrix materials, again we have plenty of options, starting with polymers where they can be used at relatively low operating temperatures. But if we are going for higher operating temperatures, we can then move into low weight metals such as aluminum, titanium and magnesium. And if the temperatures are much higher, we can go either to ceramics or the carbon-carbon composites. Now moving into the types of fibrous composites, we said there is this single layer composites starting with unidirectional composites, bidirectional also called as the woven composites. But once we stack them together, that is when we get the laminates. So, when we are stacking, it could be all unidirectional, all bidirectional or a mix of these as well. But later we said not all composites are made up of continuous fibers, some of them are made up of chopped fiber. Here there is a small compromise in the properties, but the price of these composites are much lesser and now it becomes much feasible for plenty of applications. Next we looked at hybrid composites where we can have multiple materials for the fibers, or we can have a mix of continuous as well as the chopped fiber materials. Lastly, we also looked into a classification of composites where we are trying to bring all those composites and seeing how they fit in the bigger scheme of things. So, this should summarize our discussion about different materials and types of composites. In the next video, we will look into the advantages and various applications where these composites can be used. Thank you.